Welcome back to the Deep Dive. Today, we are taking on a truly monumental question, one that really defines how the cosmos is built. How do stars decide where, when, and, I guess, how to form?
It's the ultimate cosmic real estate problem, isn't it?
Yeah.
You have these possibly vast, extremely cold clouds of gas and dust just sort of scattered throughout a galaxy. And
Right.
the central enigma, the thing we're really trying to get at, is understanding how, and maybe more importantly, why, a tiny localized pocket of that material suddenly overcomes all the forces holding it up and just commits to this runaway gravitational collapse and ignites.
And that question you sent over just captures it perfectly. I mean, we think of stars as these dense, churning balls of gas held together by gravity. But if the entire cloud is governed by gravity, how is the center point, the actual core determined? Are there just random pockets of higher pressure out there in space that get the ball rolling?
And that's exactly the fundamental tension we're diving into today. The simplistic answer is that gravity is the engine. It's always there, always pulling inward.
Sure. But the actual outcome, where a star forms, how big it gets, and how quickly this whole thing happens, that's all determined by this dynamic system of traffic cops. You've got thermal pressure pushing out, magnetic fields resisting, and supersonic turbulence scrambling everything.
So our mission today is to unpack that tension. We want to pull out the core insights on star formation, from the very first trigger to the final. And this is the amazing part, the seemingly universal distribution of stellar masses.
We do, and we have the perfect visual anchor to start us off. This is that spectacular first anniversary image from the James Webb Space Telescope.
The Rho-Ophiuchi Cloud Complex. And for you, the listener, this is not just a pretty picture. It's the closest stellar nursery to Earth, and the level of detail is it's scientifically arresting.
It really is. It captures such a compressed moment in the life of a stellar cluster. You're seeing about 50 young stars in this one complex, and they're all relatively small sun-like or even smaller.
In NASA's own description, it highlights this incredible visual contrast. The darkest areas in the image are the densest. That's where the protostars are still cocooned. I mean, the density is so high there that even JWST's incredibly sensitive infrared sensors, they struggle to punch through all that dust.
And the sheer violence of stellar birth is right there, isn't it? Dominating the upper part and the right side of the image are these huge, dramatic, deep red filaments.
Those are the bipolar jets of molecular hydrogen. That is the unmistakable signature of a star that is actively forming. It's the release valve.
The release valve for what?
For angular momentum. These jets are these highly focused outflows that mark the exact moment a young star literally bursts through its natal cosmic dust envelope. They are absolutely critical because they're expelling the incredible amount of spin that got concentrated during the collapse.
So without that expulsion,
The whole system would just spin itself apart. It could never form a star.
so that one image is showing us the beginning, the middle, and the end of the collapse process all at once.
Yeah.
That's an incredible piece of data for testing the theories we're about to get into.
It's a perfect laboratory.
Okay, so to understand that moment of collapse, we first have to, set the scene. What is this cosmic nursery actually like?
Right. So stars don't form in, the relatively empty vacuum of intergalactic space. They form within these cold, dense regions of what's called the interstellar medium, or the ISM.
And the ISM, if you just looked at the average composition of our whole galaxy, what is it actually made of?
It's overwhelmingly primordial stuff. It's about 70% hydrogen, 28% helium. The rest, only about 1.5% in total, are all the heavier elements, everything else on the periodic table.
Which astronomers just call metals.
Right. They call it all metals, and these are absolutely vital. They're the building blocks for planets, and as we'll see, they play this key role in the thermodynamics of the whole process. They were all forged in earlier generations of massive stars that, lived, died, and then scattered their guts back into the galaxy.
Okay, so if the ISM is the general sort of galactic fog, what are the literal cradles of star birth? What makes them different?
Those are the molecular clouds, or MCs. On the largest scale, they're called giant molecular clouds, GMCs. And these are simply regions where the density gets high enough and the temperature gets low enough for atomic hydrogen, just single H atoms, to cool down and condense into its molecular form, H2.
So that transition from H to H2 is the signal.
That's the signal that you have achieved star-forming potential.
And when we say giant, we are talking about truly immense scale.
Oh, absolutely. A typical GMC is just gargantuan. We're talking about diameters of 100 light years, masses that can reach up to 6 million times the mass of our sun.
6 million solar masses.
And yet, and this is the critical part, Their average interior temperature is just 10 Kelvin.
Barely 10 degrees above absolute zero.
Exactly. This extreme cold is the primary reason why star formation is even possible. It massively reduces the internal thermal pressure that's trying to push the cloud apart.
That's the ultimate contrast, isn't it?
Yeah.
Millions of solar masses held together by gravity, and it's fighting against almost no thermal resistance.
Precisely. And while 99.9% of that mass is gas, the sources all highlight that other crucial component we mentioned, dust.
The tiny 0.1%.
That trace amount of dust acts as the cloud's thermostat. The dust grains are solids, so they can efficiently absorb background starlight. They heat up just a little bit, and then they re-radiate that energy back into space at infrared wavelengths. That is the key mechanism that keeps the cloud extremely cold and, well, mediates the whole collapse.
And thanks to observatories like the Herschel Space Observatory, we now know this isn't happening in some chaotic blob. It's highly structured. The sources point to the ubiquitous nature of filaments.
The structure is everything. Herschel mapped the entire galaxy's cold gas, and what it found was that star formation is intrinsically linked to these filaments, these elongated, dense gas structures that thread their way through the molecular clouds. They're like massive gravitational conveyor belts.
Just pulling in gas from the less dense ISM around them.
Exactly. They accumulate mass until they themselves become gravitationally unstable, and then they fragment. And they do it in this quasi-periodic way into these individual gravitationally bound cores.
And what does that tell us about the geometry of the collapse? Does the filament itself set the scale for the star?
It really suggests that, yeah, the observation that the spacing of these dense cores, which will eventually evolve into stars, is comparable to the filament's own inner width. That suggests a really powerful link. The dimensions of the filament itself seem to be setting the initial size of the stellar embryo.
Okay, before we dive into the physics of how those cores actually collapse, let's just quickly frame this with the three-star populations. The sources give that context for the universe's history.
Right, it's like a stellar pedigree. We start with population Third stars. They are entirely hypothetical, we've never seen one, because they formed first from the pristine hydrogen and helium left over from the Big Bang that were completely metal-free.
And then came population 2.
Yep. Population 2 stars formed from the debris, the ash, of those first stars, which means they have very low metallicity. And then finally you get to population I stars like our sun. They're young, they're metal-rich, and they formed in the relatively recent past when the galaxy was already heavily enriched.
So it's the population I star formation, the kind happening right now in places like Rho Ophiuchi, that we can actually observe in this kind of detail.
Exactly. That's our laboratory.
Okay, so let's unpack this. We have a cold, structured core fragment, a stellar embryo, sitting inside one of these filaments. What is the fundamental physical law that makes that fragment decide, okay, this is it. This is the moment I commit to collapse?
That is the Jeans instability. It's named after Sir James Jeans from the early 20th century, and it is the core theoretical principle describing how hydrostatic equilibrium fails and this runaway gravitational collapse begins.
Okay, so if we picture the cloud as a kind of balloon, what are the forces defining its stability?
Well, on the one hand, you have gravity. That's the inward pull, and it's proportional to the mass of the cloud. On the other hand, you have the internal gas pressure. That's the outward push generated by the thermal movement of all the atoms and molecules.
And for a cloud to be stable, those have to be in perfect balance.
Perfect balance, that's hydrostatic equilibrium. The Jeans instability happens when the gravitational force in a region just overwhelms the thermal pressure gradient pushing out.
And the actual criterion for collapse? It seems surprisingly simple. What determines if gravity is going to win that fight?
It really just boils down to simple thermodynamic properties. A region of gas becomes unstable and collapses if it's either, extremely massive for its given temperature, or conversely, if it's extremely cold for its given mass.
And in these molecular clouds, the temperature is basically fixed at 10 Kelvin.
It's fixed. So the main driver is just accumulating enough mass in one spot to reach that critical threshold, which Jeans quantified.
Which brings us to the Jeans mass. This is the critical mass threshold for collapse.
Exactly. The Jeans mass, m sub j, is the minimum mass required for gravity to beat the internal thermal pressure. And his formula showed that mj is proportional to the temperature to the power of 32 and inversely proportional to the square root of the density.
Okay, so in plain English.
In plain English, the more massive it is, the bigger it is, and the colder it is, the less stable the cloud is. Once you exceed that Jeans mass, the inward gravitational force grows faster than the outward thermal pressure can respond, and you get runaway contraction.
But the sources also introduced the Bonner-Ebert mass as a maybe more realistic model for how a single star forms. What's the refinement there?
The Bonner-Ebert mass is a really crucial step towards realism because it acknowledges the environment. Genes just assumed an infinite, isolated cloud.
Right.
The Bonner-Ebert mass incorporates the effect of external surface pressure, this gentle squeeze from the surrounding low-density ISM. It defines the maximum mass that can be held up purely by thermal pressure, given that external squeeze.
And here is that real aha moment we wanted to spend some time on. The fact that this calculation seems to just predict the size of a single star.
That is the profound connection that makes the theory so compelling. When you plug in the typical observed values for sound speed and external pressure that we find in these stable molecular cloud fragments, the conditions right before collapse, the resulting maximum stable mass you calculate.
The Bonner-Ebert mass.
The Bonner-Ebert mass, it comes out to be almost precisely the typical mass of a single low-mass star, around 1 solar mass.
That's incredible.
It strongly suggests that this fundamental balance between gravity, thermal pressure, and the environment is what's setting the initial mass scale for stellar embryos all across the galaxy. It's just a beautiful link between theory and observation.
So once the fragment exceeds that Bonner-Ebert mass, the collapse is on. It's irreversible. Let's trace the life cycle from there. The cloud fragment collapses, but it also breaks up into smaller pieces.
That's right. It's a process of hierarchical fragmentation. It's driven by the gene's instability acting on smaller and smaller scales as the density goes up. And this just continues until the physics of the fragment itself changes in a way that stops further fragmentation.
And that happens when the core becomes opaque.
When it becomes opaque. This takes us right back to the role of dust, which we said acts as the cloud's temperature regulator.
Okay.
So initially, as the gas collapses, it radiates away the heat from the compression very efficiently. It stays cold. But as the density skyrockets around a critical density of about 10 to the minus 13 grams per cubic centimeter, the core becomes optically thick. It can't get rid of its own radiation.
It's trapping its own heat.
It's trapping its own heat, and this is where the dust grains take over. They absorb that energy, they heat up to maybe 100 Kelvin, and then they re-radiate that energy at far infrared wavelengths where the surrounding cloud is transparent. This process is what allows the collapse to continue just a bit more slowly.
And this leads to what's called the first hydrostatic core, a temporary pause in the collapse.
The FHSC, it's the initial sort of quasi-stable object that forms when that inner region first becomes opaque. The contraction is temporarily halted by the internal pressure of the gas, and the core temperature just shoots up until it hits about 2000 Kelvin.
Why is 2000 Kelvin the magic number? What makes the collapse restart?
Because 2000 Kelvin is the dissociation temperature for the hydrogen molecule. The heat literally rips the H2 molecules apart into individual H atoms. And critically, this process of molecular dissociation and then later the ionization of H and helium atoms, it absorbs a tremendous amount of the contraction energy.
So it robs the core of its pressure support.
It robs the core of its pressure support, allowing gravity to once again dominate. And the collapse continues rapidly, often at true free-fall speeds in what we call the second collapse.
And only once the gas is hot enough, with enough internal pressure from all those atoms zipping around, does it finally achieve hydrostatic equilibrium and you have a protostar. But we have to deal with the spin problem, the angular momentum.
It's a huge hurdle.
Everything in the universe spins. And if you conserve that spin during a massive collapse, you should get a wide, flat disk, not a compact star.
Yeah, the original cloud fragment might have a tiny, almost undetectable rotation, but as its size shrinks by orders and orders of magnitude, conservation of angular momentum forces that spin to become immense, the solution lies in the newly formed circumstellar disk.
Okay.
As matter flows from that disk onto the protostar, the whole system, which is heavily magnetized, produces these highly focused outflows.
The bipolar jets we saw in the JWST image.
The very same ones. Those jets carry away the vast majority of the excess angular momentum, and that's what allows the star to finally stabilize and finish forming.
So if the gene's instability and gravity are the simple engine, the sources make it very clear that the real physics is incredibly complex. You can't just use simple hydrodynamics. The gas is a supersonically turbulent plasma.
Which means we have to grapple with magnetohydrodynamics, or MHD.
I want to dive into this MHD challenge because this is where the simple physics just gets thrown out the window. What makes it so hard to model?
It's this constant, chaotic, and completely intertwined dance of three fundamental forces: gravity, turbulence, and magnetic fields. In these cold molecular clouds, we're not just dealing with high-speed gas, we're dealing with gas that's partially ionized. It's a plasma.
So the gas motion and the magnetic fields are locked together.
They're intimately linked, and we just don't have perfect analytic solutions for this. We have to rely very heavily on sophisticated supercomputer simulations to even get a handle on it.
And just how important are these magnetic fields? Are they comparable to gravity, or are they just a small perturbation on the system?
Oh, they are far more than a perturbation. They are comparable in importance to the bulk motion of the gas itself. We quantify this with something called the alpha and Mach number, which compares the gas velocity to the speed of magnetic waves in the plasma.
Okay.
And observations typically show this number is around 1 in molecular clouds. A value near 1 means the magnetic energy density is basically the same as the kinetic energy density of the gas. There are co-equal players in this game.
And this linkage leads to a core MHD concept. Flux freezing. Can you explain what that is?
Flux freezing is central to all of this. Because the gas is partially ionized, the magnetic field lines are essentially trapped or frozen to the bits of moving fluid. On the enormous scales of these GMCs, resistivity is very low, so magnetic flux is conserved. You cannot compress the gas without also compressing the magnetic field lines that are threaded through it.
If you compress the gas, you compress the field. And that compression must dramatically increase the magnetic resistance to further collapse.
Exactly. Which leads directly to the concept of the magnetic critical mass, m sub phi. This is the mass threshold required for gravity to overcome that magnetic tension.
There are two states.
Two states. If the cloud's mass is greater than this critical mass, we say it's supercritical. Gravity wins, and the cloud collapses quickly, largely unimpeded by the magnetic field. But if the mass is less than the critical mass, the cloud is subcritical.
And that's where the magnetic field really puts up a fight.
A huge fight. In a subcritical cloud, the magnetic tension actively resists collapse. And because of flux freezing, as the cloud tries to compress, the magnetic field strength just grows larger and larger, effectively preventing gravity from ever achieving a runaway collapse.
But if a cloud is subcritical, how does anything ever form? I mean, under ideal conditions, it sounds like star formation should be impossible in a lot of cases.
And that's exactly why we have to move beyond ideal MHD. The way around this is through what we call non-ideal MHD effects, specifically something called ambipolar diffusion.
Okay, what's that?
Ambipolar diffusion is the process where the neutral bulk of the gas slowly drifts relative to the magnetized ions. Think of it this way. The magnetic field is frozen to the ionized particles, but the vast majority of the gas is neutral H2. Ambipolar diffusion allows that neutral mass to just slip through the magnetic field lines.
So the neutral gas is slowly migrating inward, pulling away from the magnetic support structure that's holding up the few ions.
That's precisely it, and this diffusion process is slow. The time scales for this can be much longer than the freefall time, sometimes by factors of 10 or more.
So that's why magnetic fields act as a massive inhibitor. They control the rate of star formation.
Exactly. The field only allows the collapse to proceed on very small scales, typically about half a parsec, where the density gets high enough that the neutral gas can finally overwhelm the magnetic tension. So magnetic fields aren't stopping star formation, they're fundamentally dictating the pacing and the location of the collapse.
Now let's turn to the other major force here, turbulence, which the sources describe as this double-edged sword.
Yeah, turbulence is everywhere, and it's fast. Observations consistently show that gas velocities inside these GMCs are highly supersonic. The sound speed at 10 Kelvin is only about 0.2 kilometers per second.
And the observed speeds are much higher.
Often 10 times higher than that. It creates these chaotic, rapidly moving gas structures.
So let's start with this destabilizing role. How does all that chaos actually help create stars?
The primary effect is compression. When these supersonic turbulent flows collide, they create local, high-density shocks. And these shocks generate a whole spectrum of density fluctuations that follow what's called a log-normal distribution.
Meaning you have a lot of low-density gas, but a few very high-density pockets.
Of very few very high-density pockets. And it's only within those rare, super-dense pockets that the gene's mass threshold is met, triggering fragmentation and gravitational instability. Turbulence creates the seeds.
But on the macro scale, that same turbulence acts as a stabilizer. How does it prevent the whole cloud from just collapsing instantly?
Because on the large scale, turbulence provides a massive turbulent pressure support. This pressure stabilizes clouds that would otherwise be completely unstable based on just their mass and temperature. The problem is, turbulence is inherently dissipative.
It dies out.
It dies out very quickly. Every time you have a supersonic shock, kinetic energy is converted into heat, which is then immediately radiated away into space. So the turbulence should decay in just one cloud crossing time.
Which implies that unless there's some constant energy source pumping it up, the turbulence should fade and every GMC should immediately collapse.
That is the crucial implication. To sustain the turbulence we see, there must be a continuous energy input. The candidates are either, gravitational energy released when the cloud first formed, or, more interestingly, feedback from the young stars themselves.
Like the jets and the radiation we've already talked about.
Exactly. A self-regulating system.
We focus a lot on these local forces, but star formation is also subject to the broadest galactic environment. The sources shift focus to this idea of galactic quenching, the rapid shutdown of star formation when a galaxy falls into a massive galaxy cluster.
This is a huge environmental puzzle. Clusters are incredibly hostile places. Trillions of stars, hot, dense gas, dark matter. When a spiral galaxy like ours falls into a cluster, its star formation rate just plummets. And astronomers wanted to measure the timescale of this quenching to figure out the mechanism.
Okay, so what were the three competing theories for why the fuel supply gets cut off?
The first is called stripping. This is the most violent process. As the galaxy moves at high speed through the superheated, dense intercluster gas, that gas exerts this intense ram pressure.
Like a headwind.
A cosmic headwind, yeah. And it physically strips the galaxy's cold gas away, like wind stripping leaves from a tree. This is predicted to be a pretty fast process.
Okay, the second theory, strangulation, sounds much slower.
Strangulation, or starvation, suggests that the cold gas already inside the galaxy just gets used up, but the large halo of gas that usually feeds the galaxy is no longer being replenished. The galaxy has basically fallen out of its supply chain, and star formation just gradually fizzles out. That's predicted to be much slower.
And the third theory involves the stars themselves driving the gas out.
That's outflow. This idea posits that the powerful energy released by star formation, supernovae, stellar winds, radiation, actually drives the remaining cold gas out of the galaxy. The process self-quenches, and this was predicted to be the fastest mechanism of the three.
So the Keck Observatory was used to measure these quenching timescales across a huge chunk of the universe's history. What did the results show?
The results showed a really profound dependency on cosmic time. When the universe was young, about 4 billion years old, quenching was relatively fast. It took about 1.1 billion years.
And today?
In the present-day universe, that timescale has stretched out significantly to about 5 billion years.
So what's the implication of that? Why does the timescale change, and which mechanism does it favor?
The change in timescale is the key. A dynamic process like ram pressure stripping depends heavily on the speed of the galaxy and the density of the environment. When the universe was younger, galaxies were closer together, clusters were denser, so the stripping forces were stronger, and the timescale was shorter.
I see.
The fact that the quenching timescale is significant, it's not extremely fast like outflow predicts, and it's not extremely slow like strangulation predicts, that suggests that a dynamic external process like gas stripping is the dominant factor, especially in these dense cluster environments.
All right, this is where it gets really, really interesting for me. Despite knowing the physics of collapse, turbulence, magnetic fields, we still face two massive related puzzles that define the limits of our understanding.
The efficiency paradox and the universal initial mass function.
They're two sides of the same coin, aren't they? We understand the mechanisms that resist collapse, but why is that resistance so incredibly effective? And why, despite all this chaos, does the final product, the mass distribution of the stars, look the same everywhere?
That's a huge question.
So let's tackle the efficiency paradox first. If this whole process were purely gravitational, just based on the amount of gas we see, what should the Milky Way's star formation rate be?
If star formation just proceeded on the freefall time, determined by the average density of our giant molecular clouds, well, the Milky Way should be forming stars at a truly prolific rate, something like 250 solar masses every single year.
But the observation is dramatically different.
The observed star formation rate in our galaxy is only about 1 solar mass per year.
1 versus 250. That means the efficiency per freefall time is shockingly low. It's about 0.01 or 1%. And this universal inefficiency is seen in so many galaxies. It's a major, major challenge.
It implies that the stabilizing forces we talked about, turbulence and magnetic fields, they must be overwhelmingly powerful, delaying the collapse by factors of hundreds.
So if turbulence is the main culprit, How does the analytical graviturbulent model explain why the rate settles so precisely at 1%?
The model really hinges on the supersonic nature of turbulence and the density distribution it creates. As we said, turbulence generates this log-normal distribution of densities. The theory dictates that star formation can only happen in the very rare, high-density tail of that distribution.
The regions where local compression is strong enough or turbulent flows just happen to cancel each other out.
Exactly. Those are the only places where the gas can finally exceed the gene's mass. The graviturbulent model mathematically calculates what fraction of the total mass is dense enough to collapse within one free fall time, given the levels of turbulence we observe.
And a prediction.
The remarkable finding is that the analytic prediction for the efficiency comes out to about 0.017.
Which is almost exactly the 1%.
This aligns beautifully. So turbulence seems to be the self-regulating mechanism that keeps the galaxy from just blowing through its entire gas supply in a cosmic blink of an eye.
Okay, now let's move to that second big puzzle. The initial mass function, or IMF. This is the distribution of stellar birth masses, and its universality is just astounding.
It's one of astrophysics' greatest achievements and one of its greatest remaining mysteries. I mean, whether we look at stars forming in the ultra-dense trapezium cluster in Orion, or we look at dispersed field stars in the galactic outskirts, the distribution curve is largely the same.
Let's define its three key features for the listener.
Okay, first, there's the characteristic mass, or peak. This is where the distribution turns over, and it's found consistently between about 0.1 and 0.3 solar masses. This seems to define a minimum mass for star formation. Second, you have the low to intermediate mass slope, which is this broad distribution leading up to 1 solar mass. And third, and most famously, you have the high mass slope. This is a steep power law for stars above 1 solar mass, and it's very close to what's called the Salpeter exponent, which is about minus 1.35.
Let's look at that high mass slope first. Why that specific power law? The sources give two different competing ideas for this.
Right, so the first is the graviturbulence model again. This model argues that the power law tail is simply the mathematical consequence of that deep, high-density tail of the log-normal density distribution we just talked about.
So the IMF just inherits the statistical distribution of the turbulent gas.
Essentially, yes. The most massive stars form in the rarest, highest density peaks created by the turbulence. The specific slope predicted by the model depends on whether thermal or turbulent pressure is dominant, but it fundamentally links the mass distribution to the cloud's turbulent structure.
And the competing theory is competitive accretion, which paints a very different picture.
Competitive accretion suggests a kind of gravitational feeding frenzy. Instead of the masses being fixed early on by fragmentation, the idea is that protostars are continuously competing to draw mass from a shared global reservoir of gas.
And the bigger protostars have a bigger gravitational reach.
A much bigger reach. They draw in gas at an exponentially faster rate than the smaller ones. The theory suggests an accretion rate proportional to mass squared. It's a rich-get-richer scenario where a few massive stars grow very rapidly at the expense of all the others, and that naturally produces a power law distribution.
Okay, so that's the high mass end. What about the other major question? The characteristic mass, that peak around 0.1 to 0.3 solar masses. Why is there this minimum mass that seems to be the same everywhere?
Its universality really points to it being reliant on some fundamental microphysics rather than chaotic turbulence. The first major theory for this was radiative feedback.
How does heating from the star set the scale?
Well, as a protostar accretes mass, it gets very bright, and it heats the gas around it. And remember the gene's mass calculation, it's proportional to temperature to the 32. If you heat up the gas surrounding the protostar, you increase the local gene's mass, making it harder for that gas to fragment into yet another smaller star.
So it sets a lower limit on fragmentation.
That was the idea. But some simulations have found contradictions.
How so?
Well, they ran these complex simulations and found that even when they completely turned off the heating effect of radiation, the characteristic mass peak still formed around the same place.
So that suggests that while radiation is important for the star's later evolution, it might not be the primary thing setting that minimum mass.
Exactly. Which directs us toward what the sources suggest is the leading theory now, at least in simulations.
Yeah.
The role of the first hydrostatic core and something called tidal screening.
Okay, this sounds compelling.
It is. It proposes that the peak mass is a direct consequence of the physics involved in forming that FHSC we talked about earlier. Once the FHSC forms and stabilizes, it and its collapsing envelope become this centrally condensed object. And this object exerts a strong tidal force, a differential gravitational pull on the gas clump around it.
So the FHSC itself acts like a massive object, and that tidal force stabilizes the envelope, stopping it from breaking up into even smaller pieces.
Exactly. The tidal force acts as a screening mechanism. It prevents the envelope from fragmenting further, while at the same time allowing the central FHSC to continue accreting mass up to that characteristic scale.
And the key is its universality.
The key is its universality. The physics that determines the FHSC's initial size, the dissociation energy of the H2 molecule, the dust opacity limits, these are fundamental constants. They're not sensitive to the specific turbulence or magnetic field of the parent cloud, so the minimum mass gets set universally by atomic and molecular physics.
And finally, we keep coming back to stellar feedback as the ultimate regulator. Let's just solidify the role of those protostellar jets in controlling the final outcome.
Feedback is the bridge between theory and reality. Simulations that only include gravity and turbulence often produce results that just don't match what we see. They form too many low-mass objects, for example. The jets are crucial for injecting kinetic energy and momentum back into the surrounding gas.
They're essentially clearing the table around the forming star.
Precisely. By injecting this energy, jets regulate the density of the collapsing clumps, and they limit the overall accretion rate. Including jets in simulations is what's necessary to bring the star formation rate into agreement with that 1% efficiency we see, and they also seem to shift the mass peak to higher values, solving the problem of overproducing brown dwarfs. The whole process is fundamentally self-regulated.
Let's transition now. We have to talk about the incredible technology that allows us to even gather this data and test these theories. I mean, how do astronomers study these cold, dark, violent processes when the stars themselves are basically invisible?
Well, the challenge is simple. The dust that is so crucial to the collapse also obscures all visible light.
So we have to rely on the infrared imperative. We have to use light that can actually penetrate that dust.
That's right. Since these star-forming clouds are so cold and dense, nearly all observation has to happen at infrared, submillimeter, and radio wavelengths. These longer wavelengths just pass through the dust much more easily.
But even with infrared light, you run into this huge technical hurdle that the most abundant molecule, H2, molecular hydrogen, is basically invisible.
It's a massive problem for measuring the total mass of these clouds. At 10 Kelvin, H2 molecules just don't have enough thermal energy to excite their lowest rotational state. They're stuck in the ground state, so they can't emit any detectable radiation. This forces astronomers to rely entirely on observational proxies.
And what are the two main proxies used for mapping out the mass of all this cold, dense gas?
First is the dust proxy. We rely on that tiny 0.1% dust component. We can either look for the absorption of background starlight in the near-infrared, which tells us how much dust is between us and a background star, or we can look for the thermal radiation emitted by the dust itself in the submillimeter.
And measuring that emission lets you map the mass distribution.
Exactly. And the second, even richer proxy involves molecular lines.
This is the molecular line proxy where carbon monoxide, CO, is the real workhorse.
It is. CO is abundant, and critically, its lowest rotational state is only 5.5 Kelvin above the ground state. That energy difference is easily overcome even at 10 Kelvin, so CO readily emits detectable radiation. For most galaxies outside the Milky Way, almost everything we know about their gas comes from observing CO.
And this CO emission allows for this sophisticated inference of density, which is where the concept of critical density becomes such a powerful tool.
Right. The technical marvel of this proxy is its ability to act as a kind of density gate. The core insight is that a molecular line is only efficiently excited and therefore observably bright if the gas density exceeds its specific critical density, or N-crit.
Below that density, collisions are just too infrequent to get the molecule excited.
That's it. So, by tuning our observation to different molecules or different transitions of each with its own critical density, we aren't just mapping mass. We are effectively mapping the exact density distribution across the cloud.
Which is incredible.
Yeah.
If we see a bright line with a high critical density, we know there must be a lot of mass concentrated in dense pockets.
The exact pockets required for star formation. This technique confirms that while the bulk of the mass in a GMC is at low densities, the small percentage that is actively collapsing reaches much, much higher densities.
And how do we infer the dynamics? Particularly those supersonic motions we said were so crucial for the gravoturbulent model.
For that, we use the Doppler shift and the line width of the emission. To separate simple thermal motion from the non-thermal motion of turbulence, we need an independent temperature estimate.
And how do you get that?
We do that by observing multiple transitions of the same molecule, like ammonia or different CO transitions. By measuring the intensity ratios of, say, three different lines, we create a system of equations that lets us solve simultaneously for the density, the number of molecules, and the temperature.
And once you know the temperature, you can subtract out the thermal motion, and you're left with just the turbulence.
You're left with just the non-thermal velocity dispersion, the turbulent motion. And what this analysis consistently shows is that despite their extremely cold temperatures, the velocity dispersion is always several kilometers per second. It confirms that the internal motions are highly supersonic, often by factors of 10. That's the data that validates the need for these complex MHD models.
And finally, let's just touch on the cutting-edge tools looking deeper into time and space.
Well, the James Webb Space Telescope is fundamentally designed to pierce that veil of cosmic expansion and dust. By detecting light that's been stretched into the infrared, it lets us look at the very first stars and galaxies. It's already pushed the boundary back significantly, spotting galaxies shining just 390 million years after the Big Bang.
And X-ray telescopes are tracking the violent youth of stars that are still embedded in their clusters.
Exactly. X-ray observations are vital for taking a census in places like the Orion Nebula. Young stars, like T Tauri stars, have intense magnetic activity that makes their X-ray emission hundreds to thousands of times stronger than our sun. And because X-rays can punch through a lot of gas and dust, it lets astronomers count and study the entire population that's still hidden from optical telescopes.
We started this deep dive asking how a star decides where to form. We began with simple gravity, the gene's instability, but we very quickly found ourselves grappling with this complex web of counterforces, supersonic turbulence, magnetic fields, galactic scale constraints.
And the conclusion is that star formation is not a monolithic event. It's a complex, self-regulated, multi-scale process. The decision of where a star forms and how massive it becomes is determined by this whole hierarchy of competing physics.
So on the smallest scale, the minimum mass, that universal peak of the IMF between 0.1 and 0.3 solar masses, that seems to be fixed by the microphysics. Dust opacity, H2 dissociation, and that tidal screening from the first hydrostatic core.
And those processes are so fundamental that they basically guarantee the universality of that minimum star size. But then you move up in scale, and the total distribution of masses, that power law slope, and the overall rate of star formation, that's all dictated by the interplay of turbulence and magnetism.
The fact that the efficiency is universally about 1% shows that turbulence is this massive inhibitor, just preventing gravity from winning everywhere at once.
And magnetic fields enforce that slow pace. And then finally, on the largest scale, the whole process is regulated by feedback from the stars themselves, those jets, or by the broader galactic environment, which can quench the whole process through things like gas stripping.
So the core takeaway here is this profound contrast between a universal result and a totally chaotic process. The system is inefficient, it's violently regulated, and yet the final mass distribution of the stars it creates is remarkably uniform.
Which hints at some deep physical law driven by the fundamental properties of gas and gravity that just transcends all that local chaos.
Which leaves us with a final provocative thought. If the IMF is set so rigidly by the small-scale physics of the first hydrostatic core, which really only depends on the dissociation of H2 and dust opacity, things that are pretty universal,
then what extreme external conditions would be required to truly break that? What kind of massive cosmic event, maybe a catastrophic collision between gas-rich galaxies that radically and instantly changes the pressure, the temperature, the magnetic fields? What would it take to overwhelm those microphysical constraints and create a population of stars that is fundamentally different from our own?
could any external dynamics ever break the universality guaranteed by the physics of that first hydrostatic core? Or are those fundamental constants truly the final word in setting a star's minimum size?
Question to mull over.
A question for you to mull over in the black corners of the universe.